Let me introduce you, Paul and Mantos. Both of them are working on open source hardware for space. Thank you. I'm really excited I'm sure that you are also really excited to see and listen to the talk, An Open Source Guide to the Galaxy.
Thank you for the introduction.
The stage is yours.
So thank you. I actually met Paul last year in C3 Space Assembly, an assembly about open source space here in the Congress. And we found out that we both have experiments on board the Ariane 6 maiden flight. So we decided to team up, work together towards our road to space. When we started making this presentation, Paul found out and decided that there is a lot of space jargon going on, so he wants to make a 5-minute crash course on orbital mechanics, satellites, and rocket science. So, Paul.
Thank you. So let's go for it. So let's talk about satellites first. So the very basic thing you need for a satellite, some kind of box, something you can mount stuff to. And the second most important thing, I would say, are solar cells. So you can get power to power everything that you want to do. But because you're sometimes also on the dark side, you need batteries just to store it and use some power then. The last thing that is very, very important is communication. Because communication with Earth, you can decide what you want to do with the satellite, and the satellite can send you back data. So we have 2 antennas and a communication subsystem that is also inside the satellite. So now you have a satellite, but you don't know really where it should go. So let's talk quickly about orbits. Here we stand on Earth, one side in the sun, one side on the dark. And the first thing that often comes to mind is just to throw it up and have it be in space. But if you just throw your satellite up, it can maybe go to space if you throw fast enough. But it will always fall back down, so you're not actually in orbit yet. And then someone came to the idea to somehow throw it sideways and try to make it miss the ground. But that doesn't work unless you are extremely fast. So you need to reach roughly 8 kilometers per second, and then you are going so fast sideways that falling to the ground, basically, you always miss the ground and fall alongside the curvature of the Earth. And this is what an orbit is. And this particular orbit you see here is a low Earth orbit, so it's very close to Earth, and it has a time of about 19 minutes that it takes to go once around Earth. And in a lifetime of 5 years, this matches roughly 30,000 orbits that your satellite goes through.
I just saw that not a single diagram in our presentation is to scale.
Yeah, yeah, sure, of course. So now you know where to go, but you somehow have to send your satellite to get there. And to do this, you have to pack it up a little bit. So the antennas go and fold into the satellite because they would dangle on the rocket. And then you need to put your satellite in a box. Yeah, it would look like this. And inside of this box, on top of the box is a lid. And inside of this box are some springs. And those springs, when the lid opens, push out the satellite into orbit. You want to give it a try?
No, like this is a deployer. We call this box deployer. And
yeah,
this is a deployer for smaller satellites like this size. And you just put the satellite in the right way. Yeah. So you push the spring back, and then you put other satellites in front. You're closing the door, and then you have a mechanism that releases. No, I'm gonna. No. So releases the door, and the satellites are free to go outside to space. So this is how it works.
So now you take this deployer with the satellites inside, and you have to mount it on a rocket. And this is the top part of the rocket down here. as you can see. And there's also some other satellites and experiments put onto this rocket as well with you. And the last thing you need is some kind of enclosure to protect the satellites from the supersonic speeds of the rocket. And right here you can already see our two payloads, so the Curium satellite and the SIDLOC experiment. This experiment would stay on the rocket after launch. Well, then you need to get a rocket, put your stuff on top, and that's basically it. Now you are on Earth and you get up there. After you've done that, the door opens, satellite comes out and deploys its antenna. And the last thing you need is then a ground station. So this is what it could look like. So the satellite flies on top, your ground station moves afterwards and gets all the data. So and this, as Libre Space, we want to make as much of this technology chain open source and have it available in public.
So now that you're expert, I assume, on I'm starting the presentation from the point where you interrupt me with this course, yeah. And we, as Paul said, in the Libre Space Foundation, we are a non-profit doing, developing and promoting open source and Libre technologies for space. Our first satellite in orbit was CubeSat, is the satellite that is on the left side on the screen, and launched 2016 or 2015, 2016. And our second satellites were cubics, were like this kind of size satellites, and launched in this deployer. You can see it on the screen. And this happened 2020 on board Firefly maiden flight again. So we have a tendency towards maiden flights because they're cheap. Yeah? But our first and the biggest project, and the project maybe that we are more proud of, is SatNOX. SatNOX is a network of satellite ground stations. As Paul said, if you have a satellite in orbit, you need a ground station in order to communicate, download data, and also send commands to the satellite. So we have built an open source and crowdsourced network. At this point, it has more than 400 stations around the world. Most of them are like from hobbyist individuals or universities or companies, some owned by us. And here you can see some ground station. Ground station can be like something small, like with a small omnidirectional antenna, or like can be big directional antennas that are moving, following the satellite path in the sky, or big dishes. Like there are many options for satellites. It can be only downloading data, or we can also sending commands. And this is what we call an observation. This network orchestrates all the ground stations and know the position of the satellite, so know when the satellite passes over ground station, and can schedule an observation. And here you can see a signal coming from a satellite called, can't see, it's very small. And in order to do this, you need to know the frequency of the satellite, in which frequency the satellite transmits, and also you need to know the position of the satellite in order to know when the satellite is coming over the horizon to start recording and stop when it goes by. But you need to know the position of the satellite for another reason, which is called Doppler compensation, Doppler shift compensation. There is a thing called Doppler effect. It is very common also in mechanical waves, sound, when you're on the sidewalk and an ambulance pass by with a siren. You can hear the higher pitch sound when the ambulance approaches, and then when the ambulance goes away, the pitch of the sirens is wider. It's the same with radio frequencies, with electromagnetic radiation. So when the satellite passes over you, when approaching you, you have a higher frequency, and when goes away, you have a lower frequency. This is the characteristic S-curve of a received signal of a satellite from ground. So when approaches is higher pitched, the normal pitch is where the zero is, Like horizontal axis is time, and vertical is frequency offset of the center frequency of the satellite. So on this image, the signals are coming in a straight line because we're doing what we call Doppler compensation. We know the position of the satellite, we know the velocity of the satellite, so we remove this Doppler effect from the incoming signal in order to be able to decode the signal. But some people thought that you can do the other way. You can observe the Doppler signal and understand things about the satellite velocity and also location. So they have built a project called STRF, and they are doing fitting on orbital data over incoming signals. So here you can see two passes over ground stations, and you can see the gray line, which is a fit over the red dots. So this is a try to find a way to calculate the positions of the satellites, because at this point, this data, what we call space situational awareness, the data of the position of the satellites, the only source of information, public information at this point, is the US Space Force. It's the only state that have radars. A lot of states have radars, but the only state that shares the data public is US Space Force, and of course not Libre, it's just public. So there are points that if they decide to stop sharing, we have no data about space. So for this reason, we made, as I told, the Cubic mission. We launched 2 satellites like this, and we tried to find which is the best modulation and more efficient modulation to do this thing, do the Doppler, how it's called? It's called measure the Doppler shift and do the calculation of the orbital parameters using Doppler shift. And we talked about this mission in last year Congress with Freddie, which is over there. And at this point, somewhere at this point, ESA came into the background, and ESA made the public call because they wanted to create a protocol like the one that aircrafts use and ships use. Every ship is mandatory and every aircraft is mandatory to have a beacon on board, that beacon the position at specified time. So there are networks with antennas on the Earth that are receiving those signals, and they display the position of every aircraft on maps, and those data are free. You can go, you can set up an antenna and take, go outside and listen every aircraft that's passing by. And for aircraft, this is called ADS-B, and ships, this is called AIS. For satellites, there is no such a thing. Like, you can send a satellite without any beacon, without anything, and the only way to find the position of the satellite is to have a huge radar that can locate the satellites, but not identify them, just locate them. And one of the biggest challenges on doing that is one is the power, that ships have like order of magnitudes more power in aircrafts than satellites. A typical CubeSat is something like 10 watts or 20 watts of power, and like ships have megawatts and aircraft have megawatts. And the other one is size and mass. When we talk about a small Cessna, we talk about 500 kilos, I don't know. But when we talk about a small satellite, we talk about 200 grams or 1 kilo or 10 kilos, like for most of the CubeSats. So the requirements for this was they wanted a protocol with a way to identify a spacecraft, to determine the position of the spacecraft, small in size with minimal integration effort from the satellite operator, to be autonomous. So if the satellite goes off, the beacon should be still beaconing, independent from the satellite, power efficient, and as always, low cost. Yeah? So for the low power part, we use something that's called spread spectrum modulation using cold sequences. It's something that other low power protocols are using, like GPS and all, I think all of the GNSS constellation using something like this, is a difficult mathematical equation that, but the basics are that you get your data, you spread them on the time, and you spread them on the frequency, and you have like super low data rates. I think it are bits per second. And you also combine them with a preset gold code, a gold sequence, and then you transmit them. And if you see the transmission signal is below noise level, you cannot distinguish the signal from the noise. And the only way to distinguish the signal from the noise is to compare it with this known gold sequence. So when you compare it, you get back the data. And this is a very efficient way to send very low power signals in very low data rates. So you trade off your data rate for SNR, signal to noise ratio. So we combine all of those, the network, SATLOC network, with spread spectrum modulation and the algorithms from STRF, and we made SIDLOC. We proposed SIDLOC to European Space Agency. SIDLOC stands for Spacecraft Identification Localization. And actually is like the idea, so decided to fund us to do more research on the protocol and also do some in-orbit demonstrations. And so we started working on the protocol and some first integration for flight hardware. And very soon we found a flight opportunity to launch on board the Ariane 6 maiden flight. And the mission was to track the rocket during the launch phase and in the first orbit, because the rocket's supposed to do one round over the Earth and then crash to Pacific Ocean, like in purpose, yeah? The orbit in the Pacific Ocean. So we made our solution for hardware was this called SIDLOC Ariane, is the first integration of the SIDLOC beacon hardware actually went to space. Is very small, actually is bigger than we wanted, because Ariane wanted big connectors, like a D-9 was the smaller connectors accepted by by a rocket, yes, you cannot go smaller. And also they wanted a big grounding stud to ground it's very funny because when we are sending mail, Ariane is used to launch like huge payloads, like they have launched space, James Webb Space Telescope. So when we are starting email them, then we said that we want to mount our payload using 4 M3 screws. They send it back and said that you have to do something wrong. Yeah, it's very funny because they didn't have this experience and we didn't have the other experience. So it was a very nice cooperation. So this has a very small compact camera battery, a board with an MCU, a microcontroller that also do the power distribution stuff, and also has a board with an FPGA to do this, the whole gold sequence and data synthesize, and also transceiver to send it, and another board that is RF fronted, doing the amplification on incoming and outgoing signals to be able to receive it on the ground, and no solar panels because the mission was just for one orbit. We calculated the battery, we calculated for like double the amount of time, and we send it like this. So at this point, we are met with Paul in C3 Space, and we found out that the next payload actually was Paul. Yeah. So Paul, do you want to go talk about your payload?
Yeah, thanks so much. So our payload here was this this box here on this side. So 12U CubeSat. Here's a picture. It's like 25 by 25 by 35 centimeters roughly, and it's called 12U because it has roughly 12 liters. It's actually quite a bit more. And yeah, we first of all I want to go through with you a little bit through what is needed exactly for a satellite, like in theory, and then I want to go walk you through all the hardware that we actually built. And this very simply here on the right hand side There's on the bottom is the antenna of the satellite. Then we have a communication subsystem. The one we used is called SIDLOC comms, which is made to be very compatible with the SIDLOC network. And we have a main board that integrates a lot of the functionality, as well as battery and, of course, the solar panels. So this is like a very, very simplified block diagram of the SIDLOC comms. It's STM32 based and has a UHF and an S-band front end, and FPGA to help also with all the math behind it. This is then connected to the main board. The main board integrates a lot of the functionality that a satellite needs to have. On one hand side, the attitude determination and control system. This is a system that can measure how the satellite is oriented in space, so whether it's like this or like this maybe. And it can also influence that by behaving like a magnet, like a compass basically. And furthermore, it has some payload connectors so that other people can also integrate hardware into it and measure some things, whatever they want, really. And we have the electrical power system. So this subsystem is also very important. It handles all the solar panels, all the battery, and measures the payloads if they are doing what they are expected to do. So yeah, let's first have a look at the antenna. So yeah, this is the antenna subsystem. As I said, it has to be folded inwards, and we also have some kind of system that can eject the antenna after it was in orbit. This system that we used here and designed here is designed for 400 megahertz operation and has a quasi-isotropic radiation pattern. This means that it's in all sides. It has roughly the same amount of RF power that it transmits. And but we would discourage the use of this because we found out that it has some problems. Then we have the communication subsystem. As I said, the SIDLOC comms. This has the dual radio UHF and S-band, and it's based on a OS called Zephyr. As you can see here, the FPGA board, the small black board on the upper side is mounted on top, and yeah. So coming to the main board, this integrates the onboard computer functionality as well as EPS and ADCS, as I said. And the 4 payload connectors, they provide a couple of different kinds of voltages and some communication systems, especially CAN bus here to allow for communication to the payloads. All of these things we not only designed but also produced. So for both of the boards that you saw before, we have each has over 600 components, and every single component has to be placed by hand below a microscope onto the PCBs, and then soldered in an oven. So there we go. So as the last thing, we have the solar panels and the battery. So first the battery, just a couple of lithium cells that you can find in many other devices. And the solar panels, they consist of over 300 individual modules, and each module has up to 10 individual cells. So we get a very high bus voltage compared to other 12U systems at 32 volts, and they also have integrated the magnetorquers and a sun sensor that can actually measure where the sun is in position to the satellite to know, to basically know what is the orientation of the satellite. And then you have all your devices that you need, and you need to go into assembly. So the one we've flown has more than 2,200 components, 460 mechanical components, and then roughly 2,000 something, 1,000 something electrical components. A lot of harness, so a lot of wires as well. And the integration here takes a couple of hours when you're well prepared. As the last step, of course, the solar panels attached to the side, and they are actually connected by pogo pins, so you don't need any cabling. This is a very, very nice way to connect your solar panels. Yeah, so let's talk about some challenges that you will face when you want to build a satellite. First of all, microgravity. You can't really test for this. You just have to do some analysis and see if everything works as you and then hope. Then you have vacuum. This one you can actually test, and in a short time you see also a picture of a funny vacuum chamber. And then there's of course radiation. So radiation from the sun in form of electromagnetic waves. So especially UV rays are quite an issue. But also, of course, something that is behaving like radioactive radiation. So particles from the sun and also particles from other faraway stars that can hit your electronics and be a problem. Then, of course, space to be big, increasingly big problem. And this has two sides. One, you need to design your satellite in a way that it can cope with the impacts. And the second is that you need to design a satellite in a way that doesn't increase the amount of space debris. So especially fragmentation is a big problem. And these things are also analyzed. And of course, you need also to go through a review process with governmental agencies to prove that your satellite will not contribute to the space debris problem.
Will not explode in orbit,
Yeah,
actually.
for example. And yeah, this is the first vacuum chamber, I think, at
Yes,
Libre Space.
yeah.
So just a small gas bottle here. And the second part of challenges are coming actually from the rocket launch. So the rocket launch has accelerations of up to 12 G, depending, of course, on the rocket a lot. And this would actually be a big problem for humans. I think you would probably pass out. And also, of course, strong vibrations from the rocket motors. Then there can be shocks from explosive bolts that are on the rocket. And the first idea that, of course, comes to mind is a sander. This is an orbital sander. And you can attach your devices and then try and shake them a little bit. And we actually measured it up to 40 Gs, so you can at least get the acceleration criteria. But then you need to go on a specialized machine that is basically an extremely overpowered 30 kilowatt subwoofer that is shaking, that is completely shaking your satellite. And yeah, so you have to hope that it all works. And when you've done all of that, and we have done all of this for SIDLOC and Curium, you are ready to launch, really. And yeah, ready for the rocket. And yeah, we had a plan.
Yeah.
So our plan was to fly to French Guiana, which is where the rockets start from that are built in the European Union, and screw our experiments on the rocket. And then we wanted to go home.
But plans, yeah?
Yes. So, but no one really had an idea what French Guiana is actually like.
No idea.
From us. We just knew that we needed vaccines. We didn't need any visa or our SIM cards because European Union. And yeah, there was supposed to be a speed trap between the airport and the rocket facilities.
Someone did make it to the speed trap, yeah? To the speed trap test, yeah?
Yeah. So, and also it's a jungle, so if you don't like spiders, just close your eyes for a second, because this was the first contact we got with any animal.
This was arriving at home. Yeah?
This was at home, yes. So it's as big as my hand, basically.
Yeah.
Okay, so spider's over now. And then we decided to take a small boat tour on the Curium River up in the Amazon rainforest, which was frankly really interesting and amazing to see all these plants and animals that are there. So within this jungle, when you drive a couple of hours, you find like huge buildings and rockets and these launch pads, multiple launch pads actually. I think they have at least 4 launch pads.
Yeah, between spiders and capybaras.
Yes, yes.
Yeah.
And this area is actually also full of wildlife. And just in the middle of them, these rockets. So our plan was here to, on this top side of the rocket, we wanted to screw number 10 and number 5, so our SIDLOC experiment and the Curium satellite. And, well,
yeah,
sometimes.
like Paul talked about plans, yes. And plans, I think, that never are going as planned, yeah? And how many of you are software people? Okay, I want to say some offensive stuff about software people, but why you want to flash last minute? Yeah, we almost stop our software guy from taking a ladder, going up to the rocket, and flashing the new update that made the RAM 30% more efficient or something. So again, we started doing some coding on site in the Airbnb, and like writing code, passing the CI, trying every piece of code on the engineering model, which is exact copy of the flight model. And at this point, we understood that we will not, we weren't able to write big pieces of firmware on the FPGA. And we wanted to do an operation on the flight model inside the Ariane space clean room with like jumper wire on the foot of a chip, like live on the flight model. Yeah. So we made it like 1 million times on the engineer model. We made like a guide, a step-by-step guide, which screw to remove first and second, and we did that, and we performed it inside the Ariane space clean room. And for some reason, no one had something to do at this point, and everyone was above us, watching like minute by minute what we are doing. And finally, we made it. The satellite was flashed with the latest firmware, the one with the memory efficiency thing, yeah. And and we needed to make some tests, like a test that the satellite actually deploys antenna, works, and transmit. And the other fun thing about Ariane space is that they used to do transmission with huge satellites with like kilowatts of power. So every time we wanted to do a transmission, we wanted to inform the safety people, and they and they used the PMR to inform the safety people, and the PMR was like double the power of the satellite. And also did the calculation, because they calculate the perimeter you need to be away from the antenna to do that. And for our experiment it was 1.2 centimeters. Yeah? So we set up a barrier around the satellite and did the transmission. Everything worked, and we started integrating actually on the rocket. We integrated in the PIP, and also we integrated Curium inside the deployer, and then we used a 30-ton crane to move to move 140 grams of payload. It's very fun because we were following this guy like slowly, like. But yes, and then we did some screwing on the ballast board, like the aluminum part that's the top of the rocket, and then we took some photos, and finally board to the airplane to go home. Yes.
Yeah.
And then.
Yeah, we had to wait 2 months, so everything had to be prepared on site for the rocket to launch. And well, we actually got a call that there was a free spot in the mission control room, and we got the free spot here, really nice. And could witness really how the feeling was in this mission control room during the launch. As well, of course, we had a lot of launch parties throughout Europe, where everyone who could watch could watch. And yeah, then the launch happened really. So we have like a 2-minute video now. Here we can see how this big house above the rocket is retracting from the rocket, and this is the main engine of the Ariane 6. Starting now with hydrogen and oxygen inside. And 2 boosters are needed as well on the rocket to really lift it up, because the thrust of the main engine is not enough.
To give for 140 gram payload, yes?
Yeah. And yeah, there's some nice slow motion footage which I think wasn't published before, and as at least in a public talk.
Are we
but
allowed?
ESA actually allows us to use some of this footage for public presentation. And yeah, here this is the line that makes the environment inside of the payload bay, and this is the top tip of the rocket basically, and there are the payloads on top. And then the rocket finally goes up, and the tension was very, very high, of course, first launch. And after some time, the boosters could detach, and we had live video from that, and everything looked fine. Then the fairing would go off after it moved outside of the atmosphere, and there was some footage even from inside of the payload bay. And then after the first stage burns up, it gets also detached, and then the second part of the rocket, so the upper stage, this is also the last stage, the second stage for the Ariane 6, could ignite also with hydrogen and oxygen fuel. And after it lifted everything into orbit, the payloads could deploy. And we finally even got a real video of Curium One deploying.
Which is better on microgravity than the experiment here. Yeah? And this is a picture from YPSat, an experiment that was on board a satellite from ESA. And at the middle of the screen, there are some white pixels that, yes, we have a mouse, yeah. It's over there, which is the antenna of our SIDLOC experiment. Like there is a thing on the top of antenna, so we saw that the antenna actually deployed. And then, thank you. And this is an image from a telescope from Thessaloniki observatory. It's called Holomontes Observatory, and you can see this is actually the Ariane upper stage, and I think the second stage on the side. And this was the actual flight path of the rocket. So starting from Guyana, then passing over northern Europe, and then going down to Australia, and actually the satellites ejected over Australia, and the payloads, our payloads started transmitting over Australia. So then we had another flight over South America, again Northern Europe, and then deorbiting in Nemo spot, they called, I think, yeah? 5 minutes, okay. And yes, we got signals from SIDLOC. And this is what we said. What? So those are the first signals from SIDLOC, and the contributor called SA2KNG that used his station in, I think, Germany or Netherlands, or, yeah, somewhere in Northern Europe to record signals from SIDLOC. This is the spread spectrum signal, and this is the signal analyzed, and you can see the characteristic S-curve from the Doppler sieve. Like inside the noise, you can see the spots that they are decoded, and we can see that we found the middle of the signal, and we calculated this Doppler sieve signal. But we're also searching for Curium, yeah?
Yeah, so 90 minutes after launch. The first observation that should see Curium, we just see this line here that is really nothing. The signal should be like a horizontal line on this plot. And we saw nothing. We thought maybe we have to wait a little bit more than we expected, or there were some problems with the ground station, but sadly, even after 2 days, we saw nothing. So there was unfortunately no signal from Curium. And we were a little bit desperate and tried different coping strategies. And then, we did this.
Making memes is what you do, yeah?
Making memes for coping, yeah. But there came a new hope, really, when there are some people that also have a SATLOC station, and they actually have a very, very big SATLOC station. From 1956, when it was built, it was the world's largest radio telescope, and is now operated by volunteers and astronauts and cameras. And they really have open data in mind and do still ongoing new discoveries. Recently, I think it was even in the media for seeing Voyager 1. And they have 2 linear polarized antennas in front feed design, basically. And they decided to take a look. And we saw a signal. So unfortunately, still a lot less, not such a good signal to noise ratio. But we were able over quite a time period to see the data, and it was even decoding. So yeah, there we go. Finally, the data from the satellite, so we could really see all the health of all the subsystems and everything except for this low power issue on the RF front end or on the antenna. We don't exactly know. We boiled it down to 2 specific problems. Was actually very fine, and we are very happy to see that everything was working as expected, really. And yeah, I think this is like a point in time where we can really thank all of the projects and all of the people that helped from this huge community and all the open source software that we used here. And yeah, that is really, really amazing. And if you, these projects are all very community driven. So if you want to talk to us, come to C3 Space, the assembly where we are at, on the first floor, and bring us all your questions.
Nice.
Thank you.
A warm applause for Paul and Antos, please. If you leave the room, please be as quiet as possible. Don't disturb the questions and answer session. So please, microphone.
Yes, in the beginning of the presentation you mentioned gold codes for the modulation scheme, which is a form of CDMA, I understood, with 2 linear feedback shift registers which are combined. But did you publish those codes? Or did the people in Dwingelo actually had the raw signal and then you had to despread the signal?
It's not my area of expertise, but the spread spectrum signal was from SIDLOC, not from Curium. Okay. So the reception was from another station, but what we did, we got the IQ data from the receiver, and we did the analysis on the IQ data. And I don't know if this is what you want to say. That is public. Yeah, you can have also the data to check them, but it's a bit power intensive if you want to say something like that. Yeah.
Okay, then please.
Hello. First of all, thanks for the very inspiring presentation here. I have 2 questions. I guess one, because the first Ariane 6 flight did not go very well. They had a booster failure, as far as I remember. They didn't raise the altitude, and the second stage is still stuck in orbit. So, do you think that these failures affected your mission? For example, maybe Curium did not deploy at all. Like, what do you think?
So, firstly, I think we saw Curium deploying, like on live stream, but actually, this failure, it was better for our mission because we had the second chance, a second orbit, so we got double the signals. So for us, was better, but yeah, yet we stuck with something, and 1.8 tons of aluminum in orbit. Yeah. Yeah, okay. And the sad thing is that we didn't have any solar panels. If you had solar panels, probably the experiment will still operate. Yeah, but we made the experiment to operate just for 1 orbit.
Yeah, I think there were 2 payloads affected by it. The re-entry capsules. There were 2 re-entry capsules, and they of course didn't get back to the ground. Yeah, yeah. But I think what is important to point out is always that all the previous Ariane rockets never had this feature at all. So it's like a really, for this test flight, I think this is the best failure they could have.
Yeah, they nailed it with the first time, and yeah, they just had this misfire on the 3rd reignition of the engine.
Okay, thanks.
Okay, then one more question.
Hi, so do you know what went wrong with Curium? What caused that high noise signal ratio? And do you possibly plan a Curium 2 or something fixing these issues?
So there were 2 possibilities. So one is that there was a possibility for soldering error in the front that would only reveal after a certain amount of use. And we tested, of course, the system, but we had other replicates where some of them showed problematic behavior. And then there would also be always a possibility of cold welding issues on the antenna deployment, so that the antennas would not completely deploy in a way, and this is also hard. It's hard to test vibration and vacuum at the same time. So this is really an issue for testing, and we would recommend to put the antennas on the outside of the satellite and make them deployable like this, so that even when they don't deploy, you would still get a signal from the antenna. So this was like one of our lessons learned, I think. And I think with Phasma there's some of the components will be used, and the learnings can really be utilized. And I know also from a couple of other missions that use the hardware from the main board. And I think there will not be Curium 2, but certainly some of it will live on.
and also the lessons learned, yeah.
Yeah. Also,
let's hope. Yeah.
And I think Phasma is really the next big mission, as far as I know, at least.
Yeah, Phasma is the next mission of Libre Space Foundation. Yeah.
Yeah, also a satellite.
Yeah.
Then I would ask Signal Angel if there are any questions from the internet. I interpret that as a no.
Okay.
Then thank you for your talk, for the videos.
Thank you.